Hello again. It's good to see you. And those of you who are online, it's good to not see you, or never mind, that doesn't sound good. It's good to have you with us too. That's more appropriate. We wish you were here. That's not to say you should be here. Oh God, here I go again. All right, never mind. I hope you're doing well. I'll just leave it that way. Okay. The first thing I wanted to talk about was homework, because it's due Friday, due-ish Friday.
Yes.
As I was saying, it's not exact. I mean, everything's negotiable in this class, and I've gotten a couple emails from people who wanted some help with some of the questions. And sure enough, I go and figure out what people had done, and some of the stuff isn't working the way it's supposed to. So I have in front of me the answers to some of the questions of the homework. That's because some of them aren't done well. Let me talk a little bit about what the homework should be, because that will help us a little bit. Particularly for the 2PL and the 1PL for the binary items. Are you kidding me? Did that not load? Oh, come on now. I had, nope, never mind. I did load. I know where it is. I'm looking in the wrong place. There it is. Okay, so sorry, I'm looking at my screen. Can everybody see this? I have the data set, and I have some syntax, and I'm going to read in, and I'm going to start doing the two parameter models. 2 parameters, not logistic, it's a 2 parameter model. 2 parameter normal ogive. It's the silly thing about ogives versus logistic. We always call it the 2PL, but we don't call it the 2PNO, which is 2 parameter normal ogive. Anyway, read in the data. I also copied one of the functions from my example to convert theta to IRT. And here's the 2PL model. I run run Lavon for it. And get some errors. That's fine. That just means that the 3 bivariate fit cell. So this is part of the issue. If you look at all the pairs of items, 3 of those cells have empty 0 values. So if you look at 2 by 2 contingency table of items, that's what's going to happen. It's a model fit issue. It's not a warning you have to worry about. If you look at your model, here's the model output. But let's talk a little bit about the homework real quick. The homework. Let's all just agree that the 2PL fit better, right?
Yep.
No one's asked me questions about that yet, so glad on that. There we go. Which item is the most discriminating? You can tell. How do you tell that? Let me ask you. What's the most discriminating item?
9?
Yeah, but where do you get that number from?
And the estimates.
The factor loadings, that's
Yes.
right. The factor loading is synonymous with discrimination.
Yes.
And item 9 has the highest factor loading, so therefore it has the highest discrimination parameter. And if you wanted to check that, I have this. If I take my Lavon estimates and send them to my convert theta to IRT function, I can take a look at the discriminations it spits out, the A parameters, and you'll see item 9 still is the highest. And actually, the A parameter is exactly equal to the
loading.
The loading, yes, thank you. Sorry. Okay, so doing that one all right. Which item at what value of the latent trait is that item most discriminating? Where would you find that answer?
I'm sorry. Which one are you looking at?
Where is the item? At what value of the latent trait is item 9 most discriminating? Now, to answer that question, you have to think about what the definition of what discrimination happens to be. And what is the definition of discrimination? I know Jihang is going to say the slope.
It adds 50%
at the difficulty value. So if it's the slope, it's the maximum slope for the item, right at the difficulty. Then the difficulty has to be where that item is most discriminating. So the way you can tell that, if you look at the IRT output, you get the difficulty value for the item, you get 0.705. And so if we were to plot this item, although I'm not plotting it, if I could, we'd see that the difficulty is where the slope of that S-shaped curve is the peak, and it's at 0.705.
Item 9 is IRT because
You sort of have to
item-
switch between the two, yeah, unfortunately. Okay, so now item 12, it's the first one that starts giving us issues. At a given theta equals 0, which item has the lowest probability of not being endorsed? Which, I hate the reverse-coded item. I should have taken it out and made it probability being endorsed.
1 minus.
Yeah, so let's talk a little bit about what this probability is. Actually, this is where I'll switch over to my notes real quick. Don't want to see that one. I'm in... Where is it? 906, there it is. I can't even spell it. Lecture 11, stays the 6th, 7th. All right, there we go. Make sure you vote. Democracy only works for people who show up. So.
I think only few minority of people here can.
Yeah,
vote
probably
here.
true. Probably true. And
3.
and
I
it,
would love to.
and of those people who can vote, a vast minority will actually do so.
I've got my mail-in ballots in my backpack.
And I mailed my ballot in a while ago too. So you know.
School board, right?
The school board and local, yeah, but there's some. I mean, I don't know that people on this. There can be some pretty local crazies that want to go on the school board.
I'm in Eudora. There's a total of 5 names on the ballot.
That's awesome, and you probably can just walk down the street and. All right. So how would you determine the probability that an item equals 1 given a theta value? That's what I want to know. So the answer to the question. The question is, for a given theta equals 0, what is the probability of not being endorsed? So let's go with what we do know.
Oh, that would be like 1 minus the probability. Okay.
Okay, so this is the probability is given by that crazy.
We can see it.
E to the power of A times theta.
Well, let's do it in loadings and thresholds first, because I found that the M plus code, or not the M plus, the Levon code is a little bit easier to work to. But if this is for an item in person, and this theta is for a person, it's negative tau I plus lambda I times theta for the person. All right, so that's the inside here is where the essentially the model goes, right? So this is also equivalent to if we did this in the IRT formalization of A for the item times theta for the item, and I'll get it right this time. Theta for the person minus B for the item. Right? Are we cool? So there is how you can figure it out. So now, if theta equals 0, if we wanted to find out the following, the probability that y equals 0 given theta, that would be equal 1 minus the probability that of theta equals 1 of theta, right?
Yep.
We can do that. And we know theta equals 1. If theta equals 0, what do we end up getting? Well, we either have this term theta right here goes away, so we get a times negative b, or you could just go with the top part goes away and you just plug in negative the threshold. Right? So what it should be is we should be able to go look at for all of the items, and I've done it right here. This right here is a times negative 1 times a times the threshold. This is the list of that. I was just calculating this myself. That's this term right here, this version right here, using the IRT, the discrimination difficulty parameterization. I went and grabbed all that. So this right here talks about, this is in this case, the probit or the z-score that goes with the probability of a correct response for an item. And if we wanted to go and figure out what the probability attached to that happens to be, in R, that is something called the p-norm function. All right, so if we did p-norm itself, this talks about the probability each of the item responses would be equal to 1 at theta equals 0. All right, So if we wanted to figure out which one of those gives us the lowest probability of not being endorsed, so we would need 1 minus this to give us the probability of a 0. And if we wanted to figure out which one has the lowest response, I can be lazy and go in R, and I've got some code. There's a function called which.max, and it tells us it's item 9. All right. Yes, it tells us that. There we go. So I have item 4. So in your homework, put item 4. All right. So I'm showing you how you should have done it to get to the steps for it. And then I screwed it up somewhere on the back. I was trying to. I'm in Mac, R, SAS, and ASP, and my problem is to transfer a number wrong. I haven't been able to remove some of those systems. Like if I can get, here's where I'm at. If anyone knows ASP code for web services, it's even before .NET. It's the ASP standard before that. This is like turn of the century web programming. Put those. If you're old like me, put those words together. Turn of the century HTML. All right. But the thing about it is it uses an access database. Well, I'm a complete Mac and Linux user, and access databases, there's not a driver that I can find that will convert to that. So if anyone knows how to get ASP code to open a MySQL database, let me know. Because I can create databases in MySQL, I can create databases in SQLite, I can do all the other database formats for the most part. I just have to figure out what drivers ASP allows me to use. The thing I'd really love to do is convert all this to PHP, but I don't have the time, especially now. So anyway, my apologies. Long story short, I'm trying to tell you why I screwed up. I don't have the attentional focus it requires to go through each, and I apologize to you. It's frustrating, but I'll get it straightened out, particularly the first time through. Michael, you were in multivariate when I was making a lot of mistakes. This next year's multivariate will have those mistakes mostly removed.
That's pretty impressive.
So, but it was the first. Yeah, well, the other thing we're doing here is we're going from M+ to R, and so I'm trying to convert 2 different systems over. So it's just a mess right now. Anyway, I appreciate your patience. Put 4 in. Let's talk about the next item. For that item, what is the probability of not being endorsed at theta equals 0? So that is the actual probability that goes with it, and you can see. Actually, no. What did I do? I think I did that wrong. What is the lowest probability of not? I need which.min to tell us the low probability. Which.min tells us it's item 12. Yeah, I was telling you which has the highest probability of not doing endorsed. Item 12 is the lowest probability of not being endorsed. And the probability associated with that, if we just go back to this 1 minus the probability here, that probability is 0.218. And as you'll see, that is not what it should be. So in your homework for item 13, put 0.003.
And is that what the probability of 4 actually worked out to be?
No, it's not what it happened to work out to be. It may have been. I don't know. I didn't try it. I'm just done with item 4. Done with it. I'm actually done with almost all of this stuff. So, no, it's not true. I have some patience left, but no, I don't have any patience for. If you get frustrated with it, I know I can vent with you. We can making you do this. I still think it's better than me like trying to hand score your homework because I would miss half of these anyway, or I'd put a big check on the front, and that doesn't do you any good either. So at least you're focusing on it, even if it's frustrating. Item 14, how much theta does it require, does that item, so this is now item 12, require to be endorsed at 50% probability? Well, you get the answer to that item. If you knew it was item 12, if you go back to R, the 50-50 part is what? The item difficulty. So if we look at the item difficulty for item 12, we would find the answer there, which would be negative 1.997. And for us, you'll see the online system thinks it should be negative 0.2 2.743. So, in your homework for item 14, negative 2.743. I'm saying that trying to like emphasize it. So if you're going back to this at a later date and time, the beginning part of the video today, here you go. Okay? Now, finally, item 15, which item requires the most theta to be endorsed at a 50% probability? So now this is the other problem. This is looking for the this is the probability of theta item equal 1, not the probability of 0. So that's a confusing thing I could have cleared up, and I didn't. The probability that item equals 1 comes from that original model equation. I can show you, maybe. Coming. Just thinking about it. There it is. Right here. This is the probability of, well, again, this is the probability of item equals 1. And if I need to erase some of the stuff here, I need to get theta back. It's theta for the person minus b. We know if this whole middle term right here is 0, this probability equals 0.5. So we're looking for the item that requires the most theta to be enforced at a 50% probability, which would indicate the bigger the theta, the bigger the item difficulty. So we're looking for the item with the biggest item difficulty.
Are we supposed to be using the probit function or the inverse probit function or the inverse?
Inverse probit on all of this. Yeah, the logit is something that we can't do with any of this because it's Levon only uses probits. So if we wanted to figure out the one with the biggest difficulty, we could do which dot max. Excuse me, a pencil in my mouth. B. It's item 3. Item 3 should be the answer. And if we look at what item 3 gives us for it, item 3 gives us a value of 1.9 for its difficulty. So it needs a theta of 1.9 to give you a 50% probability. And that is correct. But I'm still going to give it to you. Because the next question about the probability of that item being endorsed at theta equals 2, so that makes you go back to the formulae and plug in a 2 for theta. But here's the problem. If you do that using the IRT formulation, it gives you not enough digits to give you a precise answer where I calculated it from the discrimination, or the threshold, and the loading from Levon. And so because of that, if you do that, in R, you're going to find, this is the p-norm function of it right here, you're going to find your probability is 0.521, whereas it really should be 0.525. So the answer to item 16, you can find, but you just use the Levon output, or 0.525.
What did you say was a way to go between the probabilities derived from the inverse logit function and the probit function? Wasn't it like times
1.7, if you take logit, if you put a 1.7 in the logit function equals the probit, or the opposite, well, it's roughly equal, and it's not exactly equal, and where it varies depends on where you're at in the curve. The opposite direction, if we were in probit land and we wanted to use logit estimates, we'd take the estimates and divide by 1.7. So
I just had the logit version of this answer, so I just wanted to see how close.
How close do you have?
Yeah. 0.513.
Okay, so yeah, it's in the ballpark, but not.
Yeah, it might not have gotten quite there.
Yeah, so 50, a little bit more than a 50-50 shot, and that's because remember the item difficulty for this item was 1.9, and the theta of 2 is just slightly bigger than that item difficulty, so it's slightly more than a 50-50 shot. So yeah, I screwed up my life, screwed up yours. It's one of these problems. Sorry. I'm sorry. I'm just going to.
Okay.
I'm going to apologize because
This
that's
is a learning.
for all of us.
Hopefully you can show the question and the R.
Yes, that's what I'm trying to do. I'm trying to make it more of a let's tie to how you should have been looking at this and then go into it. So I am sorry. There, I said it. I said it. It's okay to apologize sometimes, right? Right. And so this is a time where if you did waste a lot of effort on this, I really am sorry, but I hope that it caused you to play around for a little while and be like, ugh, wait a minute.
No, I'll never forget the inverse logit function.
Well, at least there's something there, right? Okay. Other thoughts or questions on homework while I have you in front of me? I haven't tried the remaining questions, so if you find issues with that, double check once or twice that there's something not else with your output, but then send me a note and I'll try to get back to you. Send me a note with your syntax, really. That'll help me troubleshoot faster. I have not troubleshot this. I may have seen a question or two. I'm trying to remember exactly. But I think this one is fairly direct in that you form the model syntax and you with different items, but then you're comparing models. You're not necessarily plugging things in to figure out the probabilities as much. I don't know that we ever do that very often. So what I will tell you is if you're in a situation where you're doing this for a paper or for a study, where we do things a little bit more is we plot them, particularly for the polytomous models. So grab that syntax of mine that plots the item for you and use it. And then you can take a look at your item response curves. Okay, the other thing I'll tell you, again, if you are not in a position where you can submit this by Friday, no problem, I will fix it. The other thing is that the database on here has the wrong date, so if you submit it, it may say that you're late, but you're not going to be late. There's going to be no points taken off. I will put the points back on the flip side of it, where I go and compile the grades. Jihong.
Could you a quick check the number 18 question?
I don't have the code for it. Oh, let's see here.
It's just the residual.
Oh, that's right. You know what? Did I do something wrong? Okay, item section 3, 2-parameter single. Which p-value is the test of close to this? And you want to know what the residual covariance between these items are? Yeah, I do have the syntax. I can fix that real quick. This is for the model that fits better. So it should be model the 2PL. The residual covariance is between items 11 and 23. B11 double tilde B23 is how you do that. The estimate itself will come out in the output when you rerun the analysis. And the value I have in my analysis, it doesn't mean it's right for what we have, is, let's see where it is. Variances, thresholds, intercepts, there it is. This one, 0.755, is the value. And it worked. So there you go.
Can you go back to our
Yeah.
output?
Yeah. So again, it's the same place you'd find the residual covariance in Levon if you were doing this with the CFA model. So it's just the covariance section. So. Okay. One last note about that residual covariance. Because we're using this limited information estimator, it's the only way we can add a residual covariance to an IRT model right now. The maximum likelihood estimates don't give you this option. And the reason for that is it treats each item independent conditional on the factor, and it builds this very long, maximum likelihood builds a big likelihood function with the product of items. Whereas the limited information build does not do that. It creates this effectively a correlation matrix and does factor analysis with it. And because of that, there's a residual covariance matrix that gets tied to it. Okay. Everybody okay? Doing all right? Nobody's walking out in frustration yet. Yes. Number 20 I can't talk about today, but I can talk about Thursday. Yes. If you have questions about that, email me them, and maybe we can talk Thursday, okay? Thank you. Any other questions or thoughts? Okay. Actually, I can talk about it. Sorry, Bishi. I
Ready
can
to
talk
respond.
about it, but I won't be able to do it. How many items are there? So it says here, for the unequal loadings
24.
in the greater response model, how many parameters are estimated? So to answer that question, you need to know how many factor loadings and how many thresholds there are. So how many there are 24 items in the analysis. So how many factor loadings with one factor?
24.
24. Each item gets a factor loading. And the question of how many thresholds you need to figure out how many thresholds per item. Now, all the items are on the same 6-point Likert scale. With a 6-point Likert scale, how many thresholds are there? 5. And since they're all on that same scale, there'll be 24 times 5 thresholds. So the answer to that would be 24 times 5 plus 24, or 24 times 6. So yes, I can actually talk about that one. The only reason I was going to say I couldn't do it is I didn't have the syntax ready, which should be 144.
Because, yeah, you added 2.
And it works. So,
Yep.
okay. Do you ever see where I got that from? Yeah, I can't talk about like the minimum function test statistic or the unstandardized parameters, but I certainly can talk about.
No, do them in your head.
What's that?
So do those in your head too.
No, those are not going to work. Otherwise, the other ones would have been right. Oh boy, comedy of errors the last couple of weeks. Yes, Miami.
It was 24 times 6, right?
24 times 6, yeah. The 24 factor loadings and 24 times 5 thresholds. But because the number 24 shows up in both, it'd be 24 times 6. Okay. Everybody excited? We're about to move on. Who wants to do some structural equation modeling? Michael does. That was a solid... No doubt about it. Almost made me say, do you have a question?
I don't know how
I'm like, no, I just asked a question. What was that?
I said I have to know how to do my dissertation.
Okay. And you're doing. When is your dissertation due?
Spring sometime.
Okay. So it's not like next week. Yeah, he told me we'd get there, but we just never did. We didn't do SEM in the SEM class.
And you're on my committee. So
Oh, even better. Am I? No, I'm just kidding.
So ask some questions you didn't teach.
No, this is good. This is good. Okay. So what we're going to get into today is a topic called, this is lecture 7. You should be able to find the new slides and all the other materials on the website. But what we're talking about is something called measurement invariance. But really, it starts with the idea of the following. Let's imagine you have a factor. Let's call it, I don't know, gambling, just for the heck of it, since you're used to that in homework. And you have 2 groups of people. All right? You've got students and non-students. This is setting up homework 6, by the way. All right. So you have the factor. This is gambling, and you've got students, and you've got non-students. All right. So the question that you might want to ask is, does gambling differ? Does the amount of gambling, I guess is gambling interest, the gambling factor differ across the groups that you have? Right? That seems a pretty straightforward thing. Or if you've got, let's just imagine, if this were the case, if you wanted to check that, how would you check? If you just observed a person's latent variable, if you could observe it, how would you go and test whether or not it was different across the groups? If you wanted to test that, let's say, the mean for students is equal to the mean for non-students.
T-test.
You could do a t-test. But we're not in the t-test world. We could do something equivalent that's in a model, a little bit more formal model. If all you had was regression, how would you do it?
All you had was regression.
Mm-hmm.
And we still have an observed variable,
Mm-hmm.
not a latent variable.
Mm-hmm.
With dummy code.
Yeah, there we go. Gambling for the person is equal to beta 0 plus beta 1. And this is the status. We could just call this like student. All right, so this would be for the person. So this would be a 1 equals 1 if a student. And equals 0 if not. Right? And then maybe we have some error out here for the person. This would be a regression analysis. You'd take a look at this parameter right here. You'd find its p-value. Maybe do a Wald test, right? Maybe do whatever the sums of squares does. Whatever they are, they should be removed from our classes, but that's an argument with me and our colleagues. Next thing, but sure enough, why can't we do that? Why can't we just output the factor score and do that? Let's talk about it.
Model fit.
Model fit, possibly. Even let's imagine we have great model fit. Like even dare I say, it's a 3-item gambling scare. It's perfect model fit. And where are we going with this? Output the factor, do this. What happens to the estimate if I output the factor and I predict it? This has measurement error.
Yeah, especially if you're
Right, yeah, with 3 items, the reliability of it's likely to be fairly low.
not taking that into account.
That's right. Or if my items were binary, I might have measurement error at different parts, like that IRT issue where we had the standard error based on theta. Right? So it may even be differential. So measurement error will end up causing us to have parameter estimates that are biased in the subsequent model. It'll also shrink the standard error, right? Because ultimately, it thinks you have a lot more information about the data than you actually have. So it's almost like you're pretending like your data are there when they really aren't. So that's a problem. There's another problem. Sort of comes from a factor analysis point of view. But ultimately, we are going to do this. We're just not going to do it where we output the factor score. We're going to do it simultaneously. Right? If we build our Lavon code, there's nothing to stop us from plugging in another line of it that says gambling and then put a single tilde in, which is just the regression part of Lavon, and put on the other side of the tilde the student variable. And sure enough, we could do an analysis. We could avoid the measurement error issue because we do it simultaneously. That's what structural equation modeling is. But there's potentially one more confound with that, which is you have to make sure that the factor is measured the same in each of the groups. What does that mean?
Same scale?
Well, same scale, same parameters. Right? And that brings about the problem. Let's imagine we have 3 items, y1, y2, and y3. And let's say this is person item, P1, P2, and P3, right? And we knew from our previous analysis in CFA, we had, this is for one, the CFA model would look something like this. Lambda 1 times gambling. I'll just call it G for a person. And then out over here, I'm going to put error for a person. I'll tell you why that's the case in just a little bit. We may have mu2 plus error. There should be a 1 on that one. And mu3, right? So here's the thing that we have to ensure that our structural equation model, where we do this equation, works. We have to ensure that what we're measuring in both groups is comparable. And the way that we know it's comparable is to figure out if some or all of our parameters are equivalent across groups. Now remember, with our errors, we had this residual variance psi squared 1, psi squared 2, and psi squared 3 right here. So the way we have to do that is analogous, and the way I wish software would be set up to do this for would be great if we could just, actually I'm going to build it into my package. It's going to be there, my IR package is going to be let you do this, but right now it's not. What would be really great is if we did this. If we just added more terms to each of the models, each of the equations right there, right? Maybe we had an effect of student, beta 1 times student for each item. Beta 2, 1 for student. And beta 3, 1 for student. Now, if we add that there, what happens? What does this effect do? Well, student can either be a 0 or a 1, right? What is the item intercept when student equals 1 or student equals 0? Well, if student equals 0, this whole term goes away, and we're left with mu1, or mu2, or mu3. What is it when student equals 1? Well, if student equals 1, now the things that aren't multiplying the factor would be mu1 plus beta 1, 1. Mu2 plus beta 2, 1. And then mu3 plus beta 3, 1. So effectively, you could test whether or not there was a difference in intercept across groups by testing these regression parameters right here. Now, subject to a couple other constraints that we have to talk about, but we'll get into that soon. So that's the first step. What if we wanted to test the factor loading? What type of model would that look like? What type of term would we need to add?
In the factor loading,
Mm-hmm.
beta plus beta.
Beta 1, 2 times the factor times student. It's an interaction right here. And you see what's going to happen for that interaction is that when student equals 0, we have, for instance, a factor loading. I'll just do it for item 1 here, but you can get the sense for the rest. And when student equals 1, now we have lambda 1. This is plus beta 1, 2. And all of these would multiply the factor g, right? Whereas this would just multiply the factor g over here. So again, that beta 2 here, beta 1, 2, this coefficient on this interaction would tell us whether or not there's a significant difference in the factor loading across groups as well. Now here's the cool thing. I haven't mentioned what type of items we have. This applies whether you've got continuous items, you've got CFA, you've got ordinal items, and you're doing what you're doing for homework 3 or 4, right? Whether you've got count items and you're in M+, all of that still applies. You can still build it this way. It still works. But it doesn't work. So this is the concept I'd like you to think about, right? What we have to do is establish that at least a set of the loadings are the same across groups, and a set of the means or intercepts are the same across groups. And without that, what happens is we end up in a realm where we have, we're essentially measuring different things for the different groups, particularly the loadings. The loading is a different concept altogether. So that's the setup for today. So with that, I'm going to pull up the slides. Any questions about that conceptually? Cool. What's it?
So we need to establish the loadings, the means, and the intercepts are same across groups.
That's right. We have to. So the primary thing that we have to do to begin with is we have to go and establish measurement invariance of the model parameters. That's where the term measurement invariance comes from. And there's a certain sequence of ways that we do that. In fact, in CFA, we do this in an ordered fashion. We start with loadings, then we go to intercepts, then we go to residual variances. And then once we have an established set, then we can go test the factors. So it's sort of an interesting process. It entails a ton of analyses to do a single approach. But I'll try to speed that up as quick as I can. Now I will note, this topic is called measurement invariance in the factor analytic world. But in the other parts of testing, we often call this differential item functioning. You may have heard that if you took, it sometimes shows up in classical test theory. Certainly shows up in item response theory. And there's a whole bunch of ways of doing it. The interesting part, if you compare the two approaches, if you're in a classical test theory sense, you're doing differential item functioning, but you're conditioning typically on the test score. And the problem with the test score is all the things that we just said why we couldn't do the analysis in the first place. You don't actually know. A score might have some lack of reliability, and you only have a guess as to a person's score. It's a piece of missing data. So anytime you see an analysis, like if you've heard the words Mantel-Hansel before, that shows up in like classical test theory. Anything that has to give you a score first and then go differential item functioning, throw it out. Because you already know what's the score. I don't know this score. It has to be some type of weighted version of the score at best, but there's way better ways to it. The other part is in diff, when you get to IRT, there are approaches that work fine, that work equivalently to what we're going to do in CFA. And those are something like what it boils down to is where you how you build your models in sequence. In CFA, we're going to start with, in the CFA, the measurement and variance, we're going to do it this way always, and I think it should be done this way always. Now, I can cite a paper that talks about this in IRT where it should be done this way too. But we're going to start with allowing everything to be completely different. We're basically saying each group has a different construct, a different scale altogether, and then we're going to slowly piece together the things from everything being different to things where we try to filter out what is and what isn't different and to do our evaluation of the invariance that way. So we sort of start with lots of parameters and we winnow our way down. And the reason for that is when we put lots of parameters in, it's like that saturated model in CFA, there's no other model with one class of people that fits better. So we know that model fit won't be an issue because we always have the best fitting model when we start with lots of parameters and work our way down. There's a group of people in IRT that sort of do the opposite. They fix all the items to be equal across groups. They say everything's equal, and then they free a parameter at a time. And the problem with that, fix everything to be equal and then sort of backtrack. If you only did it that way, you're starting with the wrong model, potentially. Because there are better models that fit, and then you can find that it weakens the ability of the test statistics that you're using to detect whether things should truly be different. So we're going to start with the lots of parameters, shrink down, not start with everything's equal and shrink and grow up. The paper I'm talking about was by a couple of grad school colleagues and a grad school professor of mine. 2006, there's one by Stark and Chernichenko and Drasko. And they talk about this sort of difference between the two fields. If you'd like a copy of it, I'm happy to show you. All you need to know is this is the philosophy I'm going to try to instill in you, and this is how I think it should be done in every situation. And there's a couple catches, but pretty much every way this should work, okay? So, big picture, measurement and variance. And again, I'm going to use the terms equivalently. Measurement and variance versus differential item functioning. They're effectively doing the same thing. The parameters of the model might change. Like in the CFA world, I'm going to compare CFA and IRT, but that's because those parameterizations are wildly different. Like if you take the intercept slope form and do differential measurement and variance on it, if you compare that to what you do if you did measurement and variance on the discrimination difficulty form in IRT, the difference is, remember, the difficulty value is a combination of intercept and loading, or threshold and loading, right? And so when you're doing, it's going to give you potentially different results because they're on different metrics, that's all. But either way, I don't care which way you go about doing it. My preferred way of looking at it is the threshold and slope, mainly because that carries regardless of the model that you have, right? So we're going to talk about this. A CFI, it's usually called measurement and variance, sometimes factorial invariance, sometimes measurement and equivalence. Basically, it's asking whether or not the psychometric properties of these observed items or indicators are generalizable across groups over time, alternate forms of a test, anything that you might have two things of that you need to compare. You want to make sure you're comparing the factors that mean the same thing. You want, if it's gambling in group 1, it should be gambling in group 2.
Can you go with more than 2 groups?
Yes, and actually, this is not required for it to be a grouping variable, although the vast majority of almost everything that's out there for software assumes you have groups, which is the frustrating term. So it can be, so you could have 18 groups if you wanted to. It gets harder when you have so many groups that you don't have a lot of people in each. But other than that, you can. There's no limit to what you can have. You could also, effectively, if you do it from the, when you think about it conceptually from this, now I can't find my notes, of course. The thing I was writing on my notes over there, nope, they're gone. Where did you go? I was writing on you all today. Oh, come on now. Anyway, I don't recall ever doing something to make that go away. But if you take it from that approach of the regression, then it doesn't really matter what the predictors are, right? They can be continuous, they can be categorical, they could be a ton of things. It works, it's the generalizable approach. But for whatever reason, all of our software does groups and only groups. So I wouldn't say that. M+ can do some more flexible things, but it's not great anyway for what it does, I don't think yet. So
is there like a specific N you would need to do this testing versus like regular CFA?
No, not that I'm aware of. People do it at all sorts of ends.
But then the more groups you have, you do realize.
You're basically trying to, you're trying to get an estimate of the parameters in each. So when you start having a few people in each, you're going to have harder times estimating the parameters of the model. Like you'll have things that won't converge,
Okay.
or you won't have the power to detect a difference, which in some respects is okay because, can't detect a difference, you just leave it to be constrained. But if there truly is one, it may show up later. So what do we have to do for this? There's two different types of invariants that we have to worry about. There's the item level, or the measurement model. So measurement invariants at the measurement model are where we talk about factor loadings, the intercepts or thresholds, residual variances, the residual covariances, and so forth. What you need to do then is to test for measurement invariance first before you do your factor comparison. Because if measurement invariance doesn't hold, then what happens is the factor comparison, like let's imagine I would have found that there's a difference in the students versus non-students if I went on my factor. Without doing the measure, if I just kept all the measurement model the same between the two groups and just tested the factor, that group difference on the factor may have been caused by group differences on the items, not the factor itself. So it could be the case that the result is a confound, potentially. You have big confound, which is you have to be able to disentangle differences on the factor that are truly there from differences on some of the items that might show up as well. So that's why it's so important. By the way, if you look at my dissertation, I did a brand new model that tried to look for different ways of looking at factors, and it's wrong. So
you need to go back to grad school?
Here's how you know. Yeah. Tell me about it. If I could keep my same paycheck, I'd take that lack of responsibility. Well, not that there's not a lack of it, but you know what I'm saying. But like, it's funny how like you feel like you're full of responsibility every part of your life until the next part happens, and you're like, wow, there's even more now. But no, I didn't mean that.
I teased you.
No, I'm happy with that. Well, me as a grad student had fairly little lack of responsibility compared to today. Just do a within-person deal. But yeah, I did it wrong. Here's where you know, like you really, this is not a situation I want to be in, but I've been in it before. When you are reviewing a journal article as a reviewer anonymously, and you have to put in your thing, Templin 2004 was wrong, right? So you have to basically say, yeah, don't do that and cite me for it, because that's the wrong way to do it. Oh, by the way, I'm Templin. So, you know.
You lost your screen.
Oh, I did. Son of a gun.
Rachel is a psychologist at UNC Chapel High School of Med. And she told me that if you do your best research at 30, you're not a researcher.
Yeah, it's pretty much.
So think about dissertation work.
It's not it's the beginning, even though it doesn't feel like it, especially when you get done. There it goes, hooray! It's supposed to be the beginning, not the end, right? Even though it feels like it's a...
No, but I came across another scholar who is very famous. He was criticizing his own dissertation work. I thought I knew all, but no.
Yeah. And one of my most cited papers is one of my favorites. It's in Psychological Methods, which is a hard journal to get into, and for the quant world has a fairly high impact factor, which also doesn't mean a whole lot. And it's wrong too. In fact, when I go to conferences now, I see this model show up. Dino and Dina. Jesse was in the class last year when we were talking about this. They always couple this with this other stupid wrong model. I'm like, stop using this model. Like, they see me in the audience, I'm like, stop using the model. Don't use that.
No, it's brilliant, though. You get something out there that everyone uses, and then you can attack it. So everybody knows about it, and everybody's going to believe you. So you just publish.
Oh, this is terrible work. Yeah, exactly. No, it's just, well, I mean, it reflected where we were as a field at the time, and then shortly, a couple years later, we figured out better ways, and that's why, yes. But yeah, anyway. So, long story short, it happens. We all make mistakes, and you may have done this before already. Have anybody done anyone done a regression analysis with a latent variable before, or a sum score?
With a sum score, definitely.
Did you check for measurement invariance?
Yeah.
Yeah, exactly. Did you floss last night? No, sorry.
That
Yeah, it doesn't really hurt that bad. Right? What's sorry?
Of course I flopped.
Oh, of course.
But I did not check for measurement invariance.
Okay, I'm just kidding. So anyway, technically speaking, we should be doing this every time we take a latent variable or some construct that we've done and created a number for. But do we? The vast majority, absolutely not. So see how it takes a lot of time. So here's the thing, though. You can check for it, and invariably something's going to go wrong. And what you really want to have is a few of the parameters be equivalent across groups. How many? I don't know the answer to. But I will tell you that if you're publishing in journals where people are used to CFA and measurement of variance, you will have to do this as part of the analysis to get published in those journals where the reviewers understand this. And then that becomes a sort of a how much is good enough for each reviewer. The ideal is to have everything be invariant. It's not going to happen. So you allow most of them, some subsets, but you need it to be the same to make it work. So then once you've done measurement invariance, once you check for that, then comes structural invariance, which talks about whether or not the traits have a different mean or a different, and ultimately it's distribution. We talk about means, we can talk about variances, we can talk about covariances. Ultimately, we're trying to see if things vary across groups. So one of the nice things about this, though, see you, Jesse, is that if you're doing a t-test, you sort of assume the variance is the same in each group. Homoscedasticity, if you're doing a ANOVA. This approach doesn't have to assume it. You can have different factor variances and still test the means. It's totally cool. So measurement invariance is needed. You have to have this. All right, and once you have that, it's okay to have structural, you don't have to, you can have structural invariance. You can check, you can have, measurement invariance means they're the same across groups. Structure, you can have non-invariance for the structural model. You can have factors, distributions that are widely different, and that's sort of what the point of your study might be. Men and women differ on this. Students and non-students differ on that. This is sort of where it's all leading. It's totally okay. So, how do we do this? There are a couple different options. And again, I'm sort of conflating CFA with IRT, so we're going to keep going the same. But if you have independent groups of data, if you have students versus... Jihan, yes.
Why we call the measurement invariance not measurement equivalence?
Measurement invariance is just a jargon that's used in the field. It's basically the ideal. You're trying to show that there's measurement invariance across the groups. So that's why it's called that way. We want invariance. Whereas differential item functioning is technically measurement non-invariance because it's saying the items are different in each of the groups or across levels of the variable that you're worried about. So we want measurement invariance. That's like the positive, whereas diff is the negative. So it's one of those things where if you're an optimist or you're a pessimist, right? I don't know. But that's why it's called that. Measurement equivalence is another way of talking about it. And equivalence and invariance are synonyms. There's similar meaning to it. So the independent groups, if you have an independent groups, again, you have students over on one side, you have non-students on the other. You can use what's called a multiple group model. And literally, each of the packages of software will have extra syntax that you code to go and do multiple groups. Lavon, when you get down to the function that runs the analysis, there's an option that says group equals, and you put in quotes the name of the variable that's the grouping variable. And sure enough, it does the model by group. It has a different section of output for each of the groups that you have. So I try to make it somewhat easier for you. All right. There's an alternative set of models. These were the first type of models that came about. They're called mimic models, which were the easiest thing to come about before you had to do lots of changes to software. Mimic stands for multiple indicator, multiple causes. No, there's an extra I there. I don't know what that is. But it started with like Yoraskog, I think, back in the 1970s. Or it's been around a long time. But effectively, it tests for differences in intercept only, but not differences in factor loading. So it was sort of the easiest thing to implement software-wise with existing software back in the day. But it's not necessarily something we need to use anymore. It's sort of subsumed into our approach. So that's for independent groups. What if you had dependent groups? Like, for instance, you had the same people measure over time. Or you had Form A and Form B with a set of anchor items, right? And maybe people took took both forms or something along those lines. What we end up doing is we put everything into the same model, but we have separate factors in that model. Right? So if we're looking at measurement variance across time, I was just building the example this morning. If we have 3 time points, the same items and same people across time, what we do is we trick the software into thinking there's 3 factors. There's the time 1 factor, there's the time 2 factor, there's the time 3 factor. And we go about doing measurement and variance that way. But we don't use the multiple groups because multiple groups is looking to separate data into multiple people. They're the same people. So we essentially hardwire our analysis using the factor loadings and using the parameters directly, using the parameter constraint syntax. Remember how we put labels on things in Lavon and it constrains them to be equal? There's a whole lot of labeling about to go on, right? We'll label everything. So here's an example of a longitudinal invariance model. There were 4 items at 2 different time points, time 1 and time 2. This would be the factor at time 1. This would be the factor at time 2. And what we'd end up allowing is, this is one time where residual covariances are okay. We're going to allow items at different time points to be correlated in this approach. And mainly that's essentially like our own miniature method factor. Right? Because the same item that's repeated, we're allowing them to have a little additional covariation just mainly because of exposure to the item itself. But let's start with the multiple group approach here. Let's start with measurement and variance. Remember the CFA model? There are 2 factors in this analysis, 3 items per factor. Not a lot of items, but it fits on a screen. You've got the covariance estimated. You have set the factor variances to 1. And here we're going to set the factor means to 0, but we're estimating each of the intercepts. And this was the eye of Providence, right? Sorry. By the way, I'm not trying to provide a religious preference here. I'm actually not religious at all. I'm just struck by that's the thing at the dollar bill, right? Every time I see it, I can't like not see that again. All right. So, anyway, maybe I'm pledging my allegiance to money. Maybe that's. I do like to eat indoor. I like to live indoors, so I think some amount of money is important. But anyway, long story short, I'll stop digging a hole again. This is what we end up having. We're going to start with the default of assuming that the factor mean is 0, the factor variance is 1. I'm going to walk through the steps of what a measurement and variance model might look like. The first step is to figure out whether or not, this is sort of a debated step, but this is a test of equality of the overall covariance matrix across groups. Now what is that? Remember, in the CFA model, the way we do things, we have all these loadings and intercepts and so forth. The loadings and the residual variances go to give us the covariance matrix. And so one of the easy ways to shortcut all this that became in the beginning, which was ultimately, let's test whether the covariance matrix overall is the same across groups. Because that's a really easy test we can do. And if it's not the same, you don't have. Oh, sorry. Do they differ between groups? If they don't differ, you have invariance. Hooray, you're done. But here's the problem with that, or what the usefulness with this. There's a couple problems of why that might be not useful. The first is that most of the time, those tests say there's some difference. Okay, now what? All right. And the second is that even with tests that are like the omnibus test that might say they're the same, there may be some combinations of parameters. Maybe there's a factor loading that's too big in one group, too small in the other, but it's made up for by the residual covariances or something along those lines. So it's possible to have smaller sets of parameters that are significantly different, the loadings, the unique variances in this case, when you put them all together to find no difference. But when you get down on the level of the actual numbers themselves, there are actually differences. So most of the time you don't ever see this, so we don't even bother with it. But we're going to pretend that we have 2 factors, 6 indicators, and 2 groups, right? So if we count up the number of parameters we have, again, with 6 indicators, there's 6 mean intercepts. There'll be 6 factor loadings. And then there will be 6 unique variances per each group. What am I doing wrong here? A factor covariance here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. What am I counting wrong here? Yeah, I don't know where I'm going with this. So I don't know where I counted that wrong. Anyway, move on. I'm not the arithmetic. I realized this last time. I can feel the proprioceptively my head's not working. We're just gonna. I'll count it up. We'll talk about it next time, maybe.
So the step 0 is.
Check out the covariance matrix, and we rarely ever do that. In fact, the examples we'll see would just be like, let's move on. I say most of the time you'll find differences in the covariance matrix. So the next step is to what we talk about is configural invariance. Now that's a weird word. What does configural make you think of? If you were to
Configure your video game controller.
that's it, right? So basically, in our case, what this is really meaning is the idea that the factor structure is the same in both groups, right? You want it to be the case where the same factors load onto the same items in each group, right? People just pretty much assume that overall. What you don't want it to be the case, in this case we have 2 factors. We don't want 2 factors in one group and 4 factors in another. That's not going to go over well, right? So this is what configural variances is. Do we have the same general factor structure? And again, most of the time, people just assume it, right? They calibrated an overall CFA model. They checked the model fit. They tried to improve the model fit. They tried to see where things were going wrong. And yes, it's there. So if that's the case, if they have the same factor structure, what they end up doing is they estimate group-specific models, right? So group A, group B, group C. Literally, you could be doing this in separate run analysis runs, but we're not going to do it. We're going to do it simultaneously in code. But we're allowing all the parameters to differ across the groups. Every single one. Now you'll note here, by fixing the factor variance to 1 for both of these, and the factor mean to 0 for both of these, we've enforced that the factor mean and variance are the same. But you'll note, because the factor loadings aren't anchoring the 2 groups together, that's like saying I've got 2 standardized variables. I could go and take my height in inches, and I can compare that with my weight in pounds. They're not on the same scale. But if I make z-scores out of that, comparing it with, let's say, the average height for someone my age and male should be, and the average weight for someone my age and male should be, now all of a sudden they have a mean 0, mean and variance of 1, but it's not guaranteed that they mean the same thing, right? Right? Yeah. Please.
So it sounds like mean centering from regression, so that it's easy to compare.
Yeah, that's what I was just saying there.
Okay.
What's happening here, our problem in the measurement invariance is that we have to make certain scale identification constraints to get the model to work in each group. Right? And so one of the constraints that we often make is the specific one you see here. The other one is where we have the marker item. Let's say we set the factor, one of the item loadings to 1, right? Well, the second step, once we get past the configure model, is to actually test the factor loadings. And if we have, this equals 1 in group 1, and it's also equal to 1 in group 2, then what we end up getting is we never actually test the parameter. We can't tell if it's different, whether or not it's truly there. So this analysis, we will eventually get to the part where we will test the means and variances of factors. For right now, they're sort of necessary evils. So right now, conceptually, we're just creating 2 separate models altogether, and we're going to identify them with the standardized factor. But they mean, we're not making any assumption that they mean the same thing. It could be height and weight that are standardized, like you were saying. Right? It could be 2 completely opposite variables altogether, just happen to have a mean of 0 and happen to have a variance of 1. Once we get past the second step when we talk about the factor loadings, then we can say they mean the same thing. But right now we have to leave it. Does that help a little bit? So we are going to create this first model where we have the configural invariance, where we're going to estimate everything all at once for both groups. And this is going to end up being the baseline model. There are no more parameters we can add. This is the most parameters we can have for this type of analysis, for this model, for this type of factor structure. Or we could be in the saturated model, but we're not going to do that. Effectively, the saturated model is this step 0 because it gives us the covariance matrix back, right? Right, so we'll go to step 1 here. So what we will end up doing is we'll see that if we were to do this, later on, this is the first model we want to compare everything with because it's the most general. And if any of those other models, when we start making more specific constraints, such as the factor loadings are equal, if that next model fits as well as this model, it's more parsimonious. We can throw out this model. We can now say the factor loadings are equal. Right? So we start locking down things to try to constrain them after this. So this is as good as it gets. Any questions? Okay. So what we're going to be doing is likelihood ratio tests. In M+, this is all what to do with it. This is all we call this is MLR, which is the estimator we're using, maximum likelihood robust method. But in R, I didn't put my slide in there. I thought I put my slide right there that says, how do we do this in R? The ANOVA function. The end. Right? All this is taken care of for us behind the scene in R. If you're an M+, you have to figure out how to go and calculate this and do this every time you do a model, which makes it harder. Lisa made a spreadsheet for this, and she says, you're still welcome. If you're an M+, people have used her spreadsheet quite frequently. She uses her spreadsheet. She just puts in models. But we don't have to do that. In R, we have the ANOVA function. Thankfully, that simplifies teaching this enormously. So let's talk about what this model looks like here. All right, we have, oh, you know what? I know what I was off. The thing I was counting the number of parameters we had per group on that slide. What that slide was telling me is how many covariances are there in the saturated model, or how many parameters would be in the saturated model, right? So with 6 items, there's 6 plus 1, 6 times 6 plus 1 over 2 parameters, or 54. I'm sorry, 27. 6 times 7. My God, I can't do it. This right here. This is the number of parameters. 6. This is the number of covariances. This is the number of means. 6 times 7 is 42 divided by 2. 21 plus 6 is 27. I just need to not freak out. It's like the anxiety is killing me. I don't know why I'm getting so anxious over the number 6 and 7. What? I need to lay off the coffee or something, right? Just stop it already. All right. So in the group 1, we had 27 possible parameters, and in group 2 we had 27. So that's where we get a total 54 total parameters we could have had in both groups. What we're estimating in each, for group 1, we had 6 factor loadings, 6 item intercepts, and 6 residual variances. And in group 2 we have the same 6, 6, and 6. Plus we're also estimating 1 factor covariance in group 1, 1 factor covariance in group 2. So that's where all these parameters in these parentheses come from. It means that we're estimating 38 total parameters, leaving 16 degrees of freedom. So it's good to get a count of this, particularly when you're making these model comparisons, because when you start freeing parameters, let me tell you, after fighting with Levon, and I think Levon is fairly straightforward as things in R go. I was finding more mistakes in code I've been doing over and over again. So make a mental note to count how many parameters you should have, how many degrees of freedom you should have, and then that sort of is your check to see that things are working well. But this is nicely coded syntax. Lisa built these slides. I really like them. So this is group 1. This is group 2. And when you see the double subscript for any type of parameter, that means it's unique to that group. Right? So what we're estimating here, when we see lambda 1, 1, lambda 1, 2, that's the factor loading for the first item in group 1 is lambda 1, 1. The factor loading for the first item in group 2 is lambda 1, 2. Okay. Everything's different. Everything's being estimated. The next step is to test for metric invariance. Metric invariance is also called weak invariance, but the way I like to talk about it is, are the factor loadings the same? I always forget the term metric. It never pops in my head. Someone's like, oh, scalar or metric? I always say factor loading, so that's how I like encode it. What we're going to do to test this is we're going to lock all the equate all the factor loadings in each group, make them equal. But then we're going to take one of the group's factor variance and set it to be freed. And why that happens to be is because we want the most general model we can. And once we make the constraint that the factor loadings are equal, to identify that scale in the second group, it's like having a marker item. And so we can free up that factor variance and we can estimate it. So I think that's a good thing. So here's what it looks like. Right? We have our factor loadings. You'll notice there's only one subscript now for this. Let me see. Oh, I've lost it. Okay. Anyway, that means they're equivalent. Lambda 1, lambda 2, they're equivalent across groups. So now what we've done is turned our factor loadings from 12 to 6. But now we're estimating 2 factor variances, right? Because there's 2 factors in group 2, right? So effectively, we've saved 4 degrees of freedom. So instead of having 38 model parameters, now we have 34, and we have 20 degrees of freedom left, right? So just, again, think of that as you're going. What do we do after that? We test the model fit. We use the likelihood ratio test. If that likelihood ratio test p-value is large, it indicates, sorry, the likelihood ratio test is testing the configural model, the very beginning one, the baseline, with the metric model. Factor loadings are equal. And if the likelihood ratio test has a large p-value, it's saying they're effectively the same. Right? The null hypothesis is these models are the same, or better yet, the metric model is preferred. Right? And the alternative hypothesis is we reject the metric model. So if the p-values are, if the p-value of this likelihood ratio test is high, we all applaud because you save a heck of a lot of steps, and you move to the next model and go on. But if it's not, what do you do? That's where the fun begins, right? Because effectively, remember ANOVA, the omnibus test, we're testing all the factor loadings to be equal at once, and simultaneous to the factor variances being not equal. It's a mess. But the way that we can get through it fast is to use modification indices. That makes life a little bit easier. Now, neglecting the fact that if the model fit gets worse, this is technically the wrong model. But modification indices tend to work really well in this situation. So go with there. So we find the modification indices one at a time, because they're one parameter tests, that indicate which parameter to add, which factor loading we should free. We allow that factor loading to be freed. We rerun the analysis. We check the likelihood ratio test. We hope the p-value is high. If not, we repeat. Check the mod indice, free a parameter, rerun the model, likelihood ratio test, check the p-value is high. So you can envision a scenario where you might say, yeah, I need this factor loading over here, for item 6 to be different. And then you move on. And then if you get a situation like that, it's called partial metric invariance, which means not all of the loadings, but some of them, some set of them are equivalent across groups. So that is what you're looking for. Lisa says 1+ per factor, but more is better. And the reason for that is this is what's going to help you make the claim that these factors are on the same, that mean the same thing. It's no longer apples and oranges or height and weight. It's now gambling and gambling, right, between the two groups. Okay. Questions?
How lot in reality?
Yeah.
Partial metric.
Oh yeah, almost all the time. The way, in fact, the example data that we're going to see, and I'll start here on Thursday with the example to try to put some concrete steps to it, and we'll flip back and forth between the slides. But the example data comes from the textbook from Brown, and it's non-invariant like each step, and I'm like, I'm sorry, it's invariant at each step. Like it completely works. I'm thinking, yeah, that comes from simulated data, right? So I think that's got to be the case. Maybe I'm wrong about that. It seems to be rarely the case it works. If it works, you feel relieved. Or maybe the case, the people I interact with, the people where it never works. So my population, the people I talk to, maybe in your group it's different. All right, we'll stop here. If you have a question, please ask me after class. It's good to see you. But Thursday, I will start with a refresher of what we're doing here, and then we actually get into R and play back with the models. Thanks, everyone. I appreciate it.
So Voodoo, if you have a good enough reason again, then you can use it, or
yeah, it's in this case the Voodoo.